Hello everyone, and welcome to Recitation with Sohail. Today, we're going to do problem 22 from section 4 of chapter 2 of the 10th edition of Boyce and DiPrima. So it's a three-part problem, and basically the point of this problem is to show you some of the weird stuff that can happen when you solve differential equations that are not linear. And hopefully at the end of this, you'll better appreciate solving linear differential equations because they don't have this weird behavior. So part A is that we want to verify that 1 minus t and negative t squared over 4 are both solutions to the initial value problem y prime equals negative t plus square root of t squared plus 4y, all divided by 2, with the initial condition that y of 2 is equal to negative 1. And then we also want to find out the interval on which these solutions are valid. And we see that equation 1, sure enough, is not a linear differential equation. So that should just be noted as part of the reason as to why all this weird stuff's about to happen. The first thing that I'm saying is weird is that this is a first order differential equation, right? We have a y prime and we have a y, but we don't have a y prime prime anywhere. But we're about to see that there's two distinct solutions that both satisfy the same initial value. So this doesn't happen with linear differential equations. A first order linear differential equation with an initial value is going to have exactly one solution or no solutions. So yeah, this is already the beginning of the strangeness. Now to actually verify that two functions they gave us are solutions is not too hard. We just have to plug it in to the equation and make sure everything works out. So sure enough, it will. We can go ahead and easily verify that both of these satisfy the initial value of y of 2 equals negative 1. I can see that 1 minus 2 is negative 1, so that's fine. 2 squared is 4. Negative 4 over 4 is also negative 1. So both of those check out. And now we see that the derivative of y1 with respect to t is just going to be negative 1. So if we go ahead and make use of that, we want to check that when we put y1 here, it's going to simplify to negative 1. So we'll do that. As you can see, I took the y here and plugged in y1, which is 1 minus t. And then we're just going to simplify the algebra from there. T squared minus 4t plus 4 is what we're going to get. This happens to be t minus 2 squared. And now when we take the square root, we get t minus 2. And you can see I put a little star on this equation because there is a caveat. Normally, we know that the square root has two possible values. The square root can be positive or negative t minus 2. So the reason I put that star there is we need a reason to pick the positive t minus 2. And that's the following. Square root x is bigger than 0. Oops, not x, but 0. So the square root function, the square root symbol, when we write it, by default, that means take the positive square root. So this square root symbol that we have here is going to give us the positive square root. So it will equal t minus 2 if t minus 2 is bigger than 0. And if it is equal to t minus 2, then negative t plus t minus 2 is negative 2. And then if you divide that by 2, you get negative 1. So y1 of t definitely satisfies the initial value problem. We see that as long as t minus 2 is bigger than or equal to 0, that's what's going to allow this equation star to be true. And that's going to happen when t is in the interval 2 to infinity. So that is the interval on which y1 is a solution. Then that's it for y1. Now we want to check that y2 is also a solution. So sure enough, if we take a derivative of negative t squared over 4, then we're just going to get negative t over 2. And then if we go ahead and plug in our y2, then we're just going to get square root of 0. The t squared plus 4 times negative t squared over 4 all cancels out to 0. So we'll just simplify it to be negative t over 2. So sure enough, y2 of t is also a solution. But conveniently, this solution is a solution on the entire interval negative infinity to positive infinity. So we do have two distinct solutions, and they each have their own intervals on which they are solutions. So that's all for part A. We did verify that they're both solutions, and we found the interval on which they are valid. So now for part B, we want to explain why the existence of two solutions of the given problem does not contradict the uniqueness part of theorem 2.4.2. So for that, let's quickly refresh on what is theorem 2.4.2 that we're not contradicting. So as you can see, here is theorem 2.4.2. Let the functions f and the partial derivative of f with respect to y be continuous in some rectangle where t is between alpha and beta and y is between gamma and delta, such that this rectangle contains the point t0, y0. That's going to turn out to be our initial condition. Then, if this happens, in some interval t0 minus h, being smaller than t, being smaller than t0 plus h, so some interval around t, contained inside of the interval we started with, there is a unique solution, y equals phi of t, of the initial value problem, y prime equals f of t comma y, with initial value y of t0 equals y0. So we do see that this is a nice theorem in that it's not only talking about linear differential equations, which is most of what we tend to study. This is a very large class, right? Y prime equals a continuous function of t and y, such that the y partial derivative of this function is also continuous. And for any such equation, any such differential equation, we're going to have some interval. It might be a small interval. This interval might be much smaller than the interval here that we started with, but there will be some interval on which we have a unique solution that satisfies the initial value problem. Now, okay, so now that we double checked that this is the case, let's go ahead and return to our problem. So we see that the portion of the theorem that we don't satisfy is going to be continuity of the partial derivative. So in the context or in the language of theorem 2.4.2, the function f or the function f of ty that we have in this situation is going to be negative t plus square root of t squared plus 4y over 2. We see that sure enough, if we do that, then this is going to be of the form f of t comma y. Right? So y prime equals f of t comma y. This is how we get it in the setup of theorem 2.4.2. So the function f is certainly a continuous function of t and y, or at the very least, if I look at the point 2 comma 1, which is 2 comma negative 1, which is where our initial value was, then the function is defined and it's continuous in some areas around 2 comma negative 1. Now we see that if I calculate the y partial derivative, then what I will get is this function here, which is 1 over the square root of t squared plus 4y. So this y partial derivative, if I try to evaluate it at 2 comma negative 1, which is the t0 comma y0 in theorem 2.42, then I get 1 divided by square root 0, and that's not good because 1 over the square root of 0 is undefined. So if the y partial derivative is not defined at 2 comma negative 1, then it is not continuous at that point. So it will not be continuous at any rectangle containing that point. So this function does not satisfy the hypothesis of theorem 2.4.2. And that is why we have two solutions, or that's why we're able to find two solutions, is we're not restricted by this theorem if we don't satisfy its hypotheses. Now also, maybe a slightly more sophisticated method of seeing we don't satisfy the theorem, or a method that depends more on your understanding of continuity, is to notice, instead of checking the partial of f with respect to y, is we could notice that the function itself is defined at at 2 comma negative 1, but it is not continuous on any rectangle containing 2 comma negative 1. So let's delve into that in a little bit more detail. So here's 2 comma negative 1. And now, if I take any rectangle around this point, then in that rectangle, there will be a point which is smaller, or which has a y coordinate smaller than negative 1. Maybe I shouldn't use y1 since we already had that. y1 is a function in this problem. All right, so if I draw the rectangle, I could pick a point underneath of 2 comma negative 1, and the y coordinate is going to be some w with w smaller than negative 1. And then f of 2 comma w So now if we quickly refresh, right, here was our function f of ty. It is negative t plus the square root of t squared plus 4y, all divided by 2. So here you can see I have, for f of 2 comma w, I have negative 2 plus 2 squared plus 4 times w, all divided by 2. If I go ahead and divide by 2 and simplify, I see I get negative 1 plus the square root of 1 plus w, and the square root of 1 plus w is undefined because w is smaller than negative 1. So we don't even have to calculate the y partial derivative in order to see that the hypotheses are not satisfied, but as you can see, this method is slightly more involved. Regardless, we see that the hypotheses are not satisfied, and therefore the theorem does not apply. And that is the end of part B. So lastly, we will do part C. We want to show for part C that y of t equals ct plus c squared, where c is an arbitrary constant, will satisfy the differential equation in part A, namely this differential equation. For any t bigger than or equal to negative 2c, and then if c equals negative 1, the initial condition, y of 2 equals negative 1, is also satisfied, and we get the solution y1 that we already discussed. And lastly, that no other choice of c is going to give us a solution to the initial value problem. In particular, no other choice of c is going to give us y2, the other solution that we found. So the point of part C is, normally when you solve a first order linear differential equation, you get the general solution, which is parameterized by some constant. And then once you put in an initial value, it specifies the constant and you get one particular solution out of the general solution. So what we're seeing here in part C is that we have a general solution, right? Because C is a parameter, it could be anything. And with the initial condition, we pick out a particular solution from the general solution, but we still have that second solution, and it's just not related to this general solution at all. It's just some other solution coming from who knows where. So let's go ahead and do part C. So again, we just kind of have to do the calculations. We see that if y of t is ct plus c squared, then taking a derivative will kill the c squared and turn the ct into c. And then once again, if I go ahead and plug in y of t into here, which was the right-hand side of our differential equation, then I get the negative t plus square root t squared plus 4y all divided by 2. Just distribute the 4 and simplify the algebra. Once again, notice that the part inside the square root turns into t plus 2c squared. And now we have the same little trick that we had before, where in order to get the positive square root, we just have the following. Right. Now, as long as t plus 2c is bigger than or equal to 0, then the square root of t plus 2c squared will be t plus 2c as opposed to negative t plus 2c. We genuinely get the positive square root. And then when we go ahead and do that, the negative t and t cancel out, the 2 and the 2 cancel out, and we just get c. So sure enough, this c is the same as this c, so we have a solution to the differential equation. And then if we want to also satisfy the initial value problem, then we have to satisfy the initial value of y of 2 equals -1. So if I go ahead and take my y of t and I plug in 2, set it equal to -1, then I can solve that equation. I add 1 to the other side. Notice that this turns into 1 plus c squared. So the only time a square is equal to 0 is if the thing you're squaring is 0. So c plus 1 is 0, which means that c is -1. And that verifies everything that we wanted to verify for part C. So that's all I have to say for this problem. Hopefully you liked it. And if you did, give the video a like and subscribe.